everybody, this lesson is to teach you if a bond is polar or nonpolar and if a molecule is polar or nonpolar. So first off, I have this picture of these two atoms bonding, and it is two nonmetals, and you can see that they are sharing this electron here and this electron here. So when they share electrons, it is a covalent bond. Now, just because they're sharing does not mean that they're going to share it equally. One might have more pull than another. So when one atom pulls the electrons closer to its nucleus, it's because it has more of an attraction, and we call that attraction electronegativity. If they are not sharing them equally, it's called a polar bond. So I like to think of it this way. Polar bears, they show them all cute and cuddly on the commercial, but they really, if you gave them that Coke, they'd pull it from you. Now, it's not ionic, so we're not transferring the electrons, but we're pulling. So they wouldn't share equally, they would pull. And if you have something that's a non-polar bond, I call that nicey nice, and it's equally shared between the two. All right, so here's some examples. If you look at hydrogen and you look at fluorine, you will realize that the electrons are very attracted to the fluorine, and that makes a lot of sense because if you go to table S, the table after the periodic table, and you look up the electronegativity of fluorine, it's a 4.0. It has the greatest electronegativity of any atom, so it's really going to pull electrons close to it. Hydrogen only is a 2.2, so it has nowhere near as much pull as fluorine. It's not ionic because we don't have a metal with a nonmetal. We have two nonmetals. So instead, this great pulling of electrons closer to one atom versus another is called a polar covalent bond. So look at this diagram. Here's my fluorine, and it has its 9 electrons, and there is the 10th one, this green one, that is coming from the hydrogen. So hydrogen is sharing its one green electron with fluorine's outermost electron, and we'll say this one blue one here from fluorine is being shared to fulfill hydrogen. So they're both fulfilling their valence electrons. Hydrogen now has 2, which is perfect for hydrogen because it's in period 1. And fluorine has 8 valence electrons, which is a perfect octet for itself. You'll notice I put a little negative sign over on the fluorine side and a positive sign on the hydrogen side. That's because the electrons are being pulled more to one side than another. So this side is going to appear slightly negative, and this side is going to appear slightly positive. It's not ionic, it's not really a transfer of electrons, so I can't have an all-out charge, but I can show the little plus and minus. Those are called dipoles. So di means 2 and pole means sides. There's 2 sides of this molecule. All right, let me go to my next example. This is the same fluorine and hydrogen, but I drew the dot diagram, and instead of putting the hydrogen really close to the F, it is not as close. So the electrons are certainly pulled closer to the fluorine. Here's another picture. Instead of drawing the atoms, I'm just showing that the electrons are more drawn to the fluorine side. All right, here's another example, hydrogen and oxygen in water. So oxygen has a higher electronegativity, it's a 3.4. Hydrogen only is a 2.2. So the electrons are pulled closer to the oxygen nucleus, and you can see when I do my Lewis dot diagram, I have the hydrogen's electrons much closer to the O than to themselves. When it looks like that, it is part of a polar bond. Here's the rule. So you can actually go through and do a calculation and solve and figure out if it's polar or not. You look up the electronegativity value for each atom, subtract to find the END. END stands for electronegativity difference. If that difference is 0.5 or greater, then it is a polar bond. If it is less than 0.5, then it would be a nonpolar bond. So, nonpolar, nicely sharing electrons. Here's some examples. If you have anything that's diatomic, hydrogen with hydrogen, nitrogen with nitrogen, oxygen, fluorine, chlorine, iodine, or bromine, they all equally share their electrons, because if you think about it, the math would come out 0. A hydrogen's a 2.2, the other hydrogen's a 2.2, you subtract and you get 0. So if there's no electronegativity difference, then they are nonpolar covalent bonds. And I think of that as nicey nice. These two fluorines are sharing their electrons quite nicely, and they're equally between the two nucleus. There's no pull. Here's another example. If you take two atoms whose electronegativity values are almost the same, that means that their pull on the electrons would be pretty equal, and neither would have enough to pull them closer to their nucleus. So that also would be nonpolar covalent bonding. So I want you to go through and do this chart. I'm going to show you the first one across. This is HCl, so I look up the first atom, hydrogen, and I get 2.2. Then I look up the second atom, and it's 3.2. So the difference between that, the electronegativity difference, would be 1.0, and the bond would therefore be polar because it is greater than 0.5. So I want you to go through and do the rest of this work. We'll check your answers tomorrow. And if you want to pause the video for a moment and do that, you can. Here's the next thing that we're going to look at, polar versus nonpolar molecules. So what's the difference? Here I'm looking at the entire structure, not just a single bond. So there's a lot of covalent molecules that are very large. When you eat, the food you eat is almost all covalent molecules. Sugars, proteins, lipids, all of them are very large molecules, and they're covalently bonded to each other. If you wanted to know if the entire molecule was polar or nonpolar, you would need to look at some very specific things about its structure, and just looking at electronegativity difference is not enough because we're not looking at a bond anymore. So I have these two diagrams. Here's carbon tetrachloride, so it has 4 chlorine molecules around it. And here's nitrogen trihydride. It has 3 hydrogens around it. So the first thing that you want to do is you can look at what the actual electronegativity difference is. Just for curiosity's sake, you can look up what's the difference between carbon and chlorine and find the electronegativity difference. And I think that you find that it's polar. But the symmetry of the molecule, this is definitely symmetrical. Unshared pairs of electrons on the central atom. So I go to the central atom, carbon, and it doesn't have any unshared pairs. Everything is in the role of sharing right now. If I go over here to my nitrogen trihydride or ammonia, this one's very different. The electronegativity difference will also come out polar. So calculate what it is and put it on that line. But I'm really interested in the symmetry and the unshared pairs of electrons. So this is not symmetrical. 3 sides have hydrogen, 1 side doesn't. So it's asymmetrical. Unshared pairs of electrons on the central atom. So here's my nitrogen, my central atom. It has right above it an unshared pair of electrons. That means that this molecule is polar because it has both asymmetry and unshared pairs of electrons. This molecule over here, carbon tetrachloride, is non-polar molecule because it's symmetrical and it does not have unshared pairs of electrons on the central atom. So here's my rule. The rule for determining if a molecule is polar. A molecule is polar if either of the following are true. If it is not symmetrical, and if it has unshared pairs of electrons. Now, this usually means that you have to draw your molecule, and when you draw your Lewis dot diagram, there's some things that very quickly give it away, because you're going to see right away if it's symmetrical or not. I think it's pretty easy to learn to look at the number of atoms. So when you look at the number of atoms, nitrogen with 3 hydrogens, it's an odd number. You know right away that's going to look asymmetrical. So anything that has 3 atoms attached to it is going to give you an asymmetrical shape, and it's going to be polar. Here's another thing that's a nice hint for you. If there is an atom and it has 4 of the same atoms around it, that tells you right away it's going to look symmetrical and it's going to be nonpolar. So sometimes you don't have to draw it out if you can visualize it in your head. I have another hint here. When you have oxygen, nitrogen, or phosphorus as the central atom, it's always going to have unshared pairs of electrons. So the molecule that it's a part of is always going to be polar. Here's another hint. If you go through and draw the Lewis dot diagram, it'll help you see the shape of the molecule. So, for example, water. Some people like to make water not bent, and water is a bent molecule. So what I mean by bent is one hydrogen is beneath it and one is to the side of it. If you tried putting it over on this right side instead, that's not how you draw a correct Lewis dot diagram. So you remember the placement of the dots. So electron 1, 2, 3, 4, 5, and 6. You draw those electrons onto your oxygen, and that lets you know that the two bonds with hydrogen, one will be placed beneath and one will be placed to the side, and therefore it shows you that it looks asymmetrical. Alright, the last thing that I want you to do is go through the same chart that you did, but this time you're not looking at electronegativity differences. Instead, you're looking at the symmetry of the model, and you are looking at if its central atom has unshared pairs of electrons. Using those two pieces of information, decide if your molecule is polar or nonpolar. If you have questions, make sure to write them down so you can ask me in class tomorrow.